There was such a lot of music around that I cannot resist and show where are my photos, at least a little bit of things that we did together with the imaginary team. Andreas Matt is sitting here. So we made an exhibition on mathematics and music. And the reason why I'm showing that here is that in that exhibition, actually, there was many things that you saw just a couple of minutes ago, like dissonance curves. And there you could really play with these things. And from that exhibition, we also generated an app. And now the challenge comes to switch to my, no, I do it here. I do it here. The app is called Musica. And look at the icon. The icon is it smarts and music. So, and now comes the transition to my talk, and I hope that everything works. So in the Musica app, you can see several interesting things, and among other things, you can see this beautiful object here, and this is at the same time mandala, symmetric rosette, drawn with my ornament app that I'm going to talk about in 2 minutes or so, but it's at the same time also a kind of map of the space of pentatonic scales. So I have to tell you how to read that. So you see these little flowers here, and each of them represents the 12 tones of our tone system. And you see these little leaves here, and this tells you which tones to take. And so the rule by which I chose, so essentially we're working in the space of chords here, and the rules by which I chose these flowers here is that you need 5 leaves, and no 2 leaves should be directly adjacent because that would sound bad. So you have these pentatonic scales. You see they subdivide, say, in 3 and 2 here. And if you click another one, you see there's, oh, okay, one thing, if you have 2 neighboring things, 2 things that are connected by an arc, you switch just exactly 1 note. Look at the center of the picture. And so you see you have this 2, 3 here, but you also have 1, 4, and you have an all 5. And this interesting thing is they all sound kind of different. And now, okay, that's cool. And you can actually make music with that. I won't go, okay, sorry. I won't go into the details of that, but this is actually the change to the symmetry part, because I wanted to have this thing looking nice. And for that, I used my app iOrnament. And now comes the next challenge. I have to stop this. So having this hybrid things is really kind of challenge, but now I really have to switch to my iPad for a second, hoping that that works. Do we have my iPad? Yes. Okay, so I start with a very, very, very quick demo, since I don't want to switch back and forth too often. Okay, you see my screen. So this is essentially an ornament drawing app. So the idea is, well, you choose some kind of pen, and then you start to draw, and interesting things happen. You can zoom in, you can zoom out. So you can change between the symmetry groups and say, I want to have something more square-like. I prefer the snowflake things here. You can really play with that. You have advanced things here. You see these gold pens here. So if I move my device, you perhaps see it, it's a little bit slow through. It behaves like gold. So if you look from different angles, you get different way of the light works on that. You have also kind of fill things. So I have a fill bucket, and I can say I want to fill this part here with something, but I can also, for instance, draw or fill with glitter. And if you like the hyper sparkle, you can also turn on the hyper sparkle. Behind all that, there's really serious math. And so we all three are talking about our passions today. This is more a passion project than a research project. But at every little step when you do these things, you really need math. In particular, if you say, I want to have that, and I want to have that in the hyperbolic plane with different parameters. Look how nice these things float here, or perhaps even better in a kind of square hyperbolic plane. What is that? So you see, math comes into that. And I today, in the time that is not left, want to talk a little bit about the math. So please memorize what I've shown you now, because I will refer to all these parts, and I will perhaps give a quite speedy part. So people still see me, or but not the screen. Okay, so let's share Keynote now. Can you also share the sound if you're playing? No, I don't. No longer will play sound. So, but I'm on the wrong screen here. Sorry, we didn't exercise that. So I need my Keynote. Where is my Keynote? Here is my Keynote, and I say I want to share the Keynote screen. Sorry. And I think now I'm in my talk, which is cool. The challenge of real-time symmetry drawing. So you saw all that happened rather fluent on the iPad. And so I want to essentially talk about the mathematics in my app. I want to get rid of that. How do I get that? Sorry, I want to minimize that. So here are a couple of topics that may be interesting. And you could also talk, and I already did that a little bit, about the mathematics with the app. Would be an entirely different talk. And I at least talked about the math and music part. I will talk about some of the things on the other side. Before I do so, I have to tell you why I'm doing that. So first of all, it's fun for me. I love to write programs. I love to write programs that are, in a sense, high-end. But on the other hand, it's somehow one of the most exciting things I've ever done, including several math theorems. Because it brings you together with people who are really doing interesting stuff with your software. And so before I start, I just want to show you a few pieces of art, and I really would call them art, that people created with the app. So I love this one here. Mandalas are, by the way, a very attractive thing. I love this one here. And if you look here, you have these fine shades, and this needs very, very high requirements on the fluency of your pen that you use. I cannot believe that it is done with my app, but it is done with my app. I have no idea how. So I have a wake. Okay, these little distortion lines, I think, were done with some kind of post editing, but the rest is really done with the app. And this amazes me a lot. If people are, so here you see gold pens on ecstasy, and here you have. Well, that's a great artist from Italy who does a lot of human rights things, and this was a big poster as a human rights campaign. You recognize the color symmetries here? So this is actually the same person drawn with the color symmetry option that you have in the program. This is also done with the program. And also this, and so you see here also there's a big interesting connection to knot theory. So you can do all these things, but to get people to do these things, your program has to behave as natural as possible. It should feel like you have, well, a pen or a brush and draw on a canvas, more or less. And so how to get that? If you want to get that, it becomes really hard because you have really hard real-time requirements. And I want to go in a few aspects along the rendering chain that happen here. Just a little timeline. I started the entire project a bit more than 10 years ago. And so my personal goal is to have every year one big step ahead. So every year I say, okay, I take a few weeks off and try to do one big feature. And but what do you actually have to do? So you have your Apple Pencil or your pencil here and you draw, but actually you're processing data. So you have people taking the pencil, drawing some strokes and generating sample points. And somehow you have to get from the sample points to the nice picture. Sounds simple. I never expected that it can be so difficult to draw a stroke. I don't show it now on the iPad, but you can imagine the following thing. If you have a usual drawing program, people want to zoom in and zoom out. And depending on how good the program is, they may zoom out a lot and zoom in a lot. And a big difference from iOrnament to usual drawing programs is that you have an infinite canvas. So you may say, I zoom out until my thing is very, very tiny. Then I draw a stroke and you get data points scattered all over your screen, and you have to make something reasonable out of that. On the other hand, you want to zoom in and draw the final details. So you have a scale of approximately 500 magnification factor where your pen has to operate in a reasonable way. So the rendering engine starts more or less as following. You start with a kind of stroke engine where you do what I call data thinning and data thickening. You always have to adapt to how fast is your device. So you have to measure more or less with how many data points can be processed in which time, and adapt your quality to make things reasonable. You have to do interpolation, you do the pen pressures here, you do the basic symmetry. Then from there, I switch the color because I'm going from the CPU to the GPU, to the graphics processing unit, where I do the composition of different layers, the global layout, special effects like hyperbolic things, and oh no, special effects come a little bit later. The gold is done here. Then you have deformations, and then you have the special effects like the sparkles that come on top of all that. And I want to show you, well, it's more or less what I've drawn a few minutes ago. And I want to show you what happens while you draw that. So first of all, you draw strokes. And there are, you don't see that now, but there are several approaches on how to draw strokes and how to process the data here. One of them would be, okay, you have all your big picture and you draw every copy of your stroke individually. So you do something and you draw here and here and here and here and here, and you will end up drawing about 2,000 strokes, and this takes too much time. Actually, almost all other symmetry drawing programs do exactly that. And that's the reason why they get slow at some point. The other way around would be the fully mathematical thing. You say, okay, I have some kind of fundamental cell in here. Some fundamental cell in which nothing repeats. I make copies of that over and over. This actually gets too complicated from the logic here and takes time for other reasons. So what I'm doing is actually something in between. So I take something like a translational fundamental cell, the smallest region that you just get, where you just can generate your picture by translational copies. I generate that and then I copy over and over, which can be done pretty quickly on the graphics card. It's a good way to do that, but you have to take care about many things. So what you actually do, I told you, you draw a stroke. So what you actually do is something like your pen moves from here. Oops, here you see a little white thing because your pen may cross the borders of your little rectangle, and you have to take care of that. And taking care of that turns out Well, first of all, you have to do a modulo thing. But on the other hand, if you imagine you have a blurry stroke, you very soon get artifacts that come from that the right side doesn't match exactly the left side, because your stroke, each single dot has some kind of radius, and you have to take care of that as well. So that's the first thing. Then I showed you the hyperbolic thing. There's also a spherical thing, and believe it or not, you get monotony in that thing. So you draw around a rotation center, and you have to take care about the number of times you have the copies, and you have to make some kind of tracing of what goes on geometrically. I won't go into that detail, but it's extremely interesting. One important advantage of doing that tile-based approach is that you can have a really high resolution on your tile. So imagine I zoomed out a little few minutes ago, but each of the single tiles had a resolution of 4096 times 4096 pixels, which is a lot, which you want to get the artists into that game, because they want to have extreme control. So what you actually draw is this. Next step, you somehow process your pressure, you add the symmetry, and from that, you produce some data from which later on you have to compose your image. Next interesting or important step, I won't get into the details here. You have several layers in the drawing, and so the gold pen is, for instance, a characteristic of a certain layer, and you have to compose them. You do that on the GPU, and here I added the MWL, which means many white lies, which it's way more complicated than you see here, but I won't explain it. But I want to go into the special effects. So what are you doing with the special effects? And therefore I have to teach you a little bit about what you do on your GPU. So let's zoom in here and look at the GPU. The GPU is a graphics processing unit. And well, essentially, at least one part of it, the so-called fragment shader, can be considered as a fast parallel computing device on a grid of data points. And historically, this has grown out of having fast engines for games. And so these data points have the unfortunate property that you cannot specify what you want to have in there. They are essentially four-dimensional vectors, because for having a color, you need a red, green, blue, and a transparency channel. So that's what you have to deal with. You have to map everything to something that works nice on four-dimensional vectors on such rectangular data points. That may not lead to the deepest of all mathematics, because you're adapting to something that is very, very specific in a way. But on the other hand, if you want to do that, you have to face the actual problems that arise when you have this model as a kind of unbreakable unit for your software, and you have to do it there. And many mathematical problems arise there. I just want to give you a few more interpretation of these data points. So for instance, if you only use the first two entries, you could say, okay, these are position vectors. So I do my deformations by considering color in the data points as vectors of position from where I take the color. I will come to that in a moment. You could also say it could be a position in 3D, or it could be a normal vector in 3D. We need that for the gold light effect. It could also be combinatorial data when you fill or not fill, and you should be very flexible what you can do with your 4D vectors here. So talking about the gold, what really actually happens is, well, you have drawn something, and intentionally I took a drawing pen that is rather blurry here, because what I'm in the next step do, I take a kind of mask around everything that I drew, and from the blurriness create a height field. So the more white such a point is, the higher it should be. And if I go from white to black in a smooth way, I have such a kind of curve. And from that height field, I calculate and store in the graphics processing unit a normal vector at each picture that tells me how my surface is directed. And then I do illumination geometry. So the standard things, scalar product, and things get more bright if they are hit directly. And from that, you get this effect. You saw other things here. You saw the glitter. I'm very proud of the glitter. So let's zoom into the glitter. Behind the glitter, there is this texture here, which is a kind of texture that is used for all of the glitter, which is a simulation of square particles thrown onto the floor, and in some well, viscous liquid, they tend to stop at some point with their motion and have a certain direction, which is encoded by the color here. So the color here is again normal vectors, and they get a certain shape that correlates with the direction, and this gives an extremely realistic effect of what's going on. So as a matter of fact, I went into fashion stores and observed what glitter is. Also for the gold, I spent hours standing in front of window shopping jewelry stores to see what makes gold. So gold essentially is potential. It's potential to shine bright. And so if you make that here, so this is, by the way, real glitter magnification. And then you take that again into your illumination model and you get the glitter. So I've shown you the hyperbolic thing. I started later. I have. You did. You have about like 5 more minutes. 5 more minutes. Okay, that's okay. I showed you the hyperbolic thing, and I want to make a really very, very speedy tour through what happens in hyperbolic thing. By the way, I highlighted here special parts. I already talked about the glitter. I already talked about, no, I didn't talk about the gradient fill. I won't do that. I talked about the gold. I don't talk about the hypersparkles. They are hell. And as a matter of fact, that's the slowest part in the program. And I still hate that these things that, so actually I programmed them around Christmas. And so when you're standing in front of a Christmas tree and look at it, you don't see light points. You see this kind of flares. And this is actually a cognitive effect that is not there optically. If you make a photo of that, you get something different of what you see. And what you see depends on your eyelashes and on your retina, and a very complex thing, but you see it. And if you want to have people believing what you're doing here, you have to program hypersparkles in a way. I won't explain that, but I want to explain a bit about the hyperbolic thing extremely fast. Imagine I've drawn something in the Euclidean space which belongs to a certain symmetry group, and I want to make a hyperbolic version of that. So what I actually have to do is to somehow perturb the numbers in the rotation centers. And for those of you who know Coxeter groups and all these things, you have these inverse numbers of the symmetry repetition numbers, and if they add up to 1, you get something Euclidean, and if they are smaller than 1, you get hyperbolic. If they are greater than 1, you get spherical things, and you want to have an engine that is capable of doing that quickly. And actually, we did first things like that already more than 10 years ago, but they were good but too slow for what I wanted to have. So what we actually did there, no, I don't. Okay, Schwarz's reflection principle tells you that you essentially can go back to just one fundamental cell and care about the fundamental cell. And in that fundamental cell, what we then did, we calculated a kind of grid. We did a conformal deformation with methods from discrete differential geometry. And with that, you can map this to that. Why conformal? Because this preserves the artistic content. So if you do these conformal maps, it looks as much as possible like what you actually did in the Euclidean thing, and it's just hyperbolic. So this is, I claim this is the right thing to do. And then we use this technique of color mapping. So if you say this here is a color coding of the positions of this image, this here would go to this picture here. So you can, in the color coding, encode how you want to your ornament to have. And if you, in the color coding, insert this position map, you get this thing here. So the trick is to go with the color coding. And in the old version, we had pre-computed position maps here. But now we can do that in real time. You saw that just a few minutes ago. And the question is essentially how to create such a kind of mesh. And I want to explain what we are doing here. And before I explain that, just an idea that came up at some point. If you know conformal maps, you know they have to do a lot with forces. So conformality is very often things driving into certain equilibrium. And the dream that we had was to say, we want to have the pixels swim to their right position. And it took 8 years to get the right idea how to do that. But now we can do that. And what we actually use, okay, I won't go into all the details here, but it boils down at the very end to have a kind of averaging map between these things here. And this is what another very famous person, Keenan Crane, calls the Neanderthal method of calculating conformal maps. You have to care about the boundary here. And the reason why this is Neanderthal, because it's the least sophisticated thing you can do. But in contrast to all other possibilities you can do, this parallelizes. You can do that on the GPU, which is cool because so you here see, okay, you start with some input and you have some iterations, and after 700 something steps, which is way too slow because you have to calculate all the things. No, it's not way too slow. It's just fast enough because we do it on the GPU. And on the GPU, you get essentially, you have an animation of the relaxation process. I end in 1.5 minutes. So here you see the relaxation process. This is what happens on the GPU, where you don't have these vertices as position vertices. This is the data in your GPU grid cells, which moves to the right position. We need again Schwartz reflection principle to do that. And then this can also be used to make conformal maps, say, from the circle to a square. So this, you find also, it's perhaps the oldest drawing of a conformal map, which goes back to Schwartz. But if you do it with our method, then it doesn't look that nice. So you want that, but you get that because of numerical instabilities. So you again have to dive deeper, and at some point you start to use Jacobi elliptic functions to do the deformations. Don't go into the detail, but I want to show you this picture. This picture is just one of the most magnificent pictures I've ever produced. Really, it took several days because this here is a position map with extreme high precision. So it's, I think, 2000 something times 2000 something, and maps the square to the circle. So here it's not black. It's something like this value, which corresponds to this position in my circle here. And here it's this position, and it's stored in 16-bit color depths. It's calculated in Mathematica, stored in 16-bit color depths, moved through a processing chain that doesn't damage this 16-bit color depths. Try to do image processing during a processing chain that doesn't violate your pixel accuracy. So most probably this here doesn't have 16-bit color depths, but this then can be used to let artists pieces like that, like Sepp Lester, a really famous calligrapher who just painted the logo for a space mission rocket. So he's really one of the big guys. And so he has, for instance, with iOrnament done this letter here, which we both believe is the most complex letter ever drawn in human mankind. It's incredible. It took him 6 months. And with this, I thank for your attention.